Okay, so what have we noticed? Yeah, it remains pretty much symmetrical. Now, this is unlike what we saw with the binomial distribution, you remember? Yeah? With the binomial distribution, we ended up being skewed, depending as we change the probability. Yeah? Because, of course, if you have a fixed number of trials, you change that probability, the shape becomes skewed, so either positively skewed or negatively skewed. Remember we did that yesterday? If you can't remember, go back and play with it. It's on the VLE, okay? But yeah, here, as we change that parameter, can you see that the shape becomes it stays pretty much symmetrical? So what we can say is that the Poisson distribution is basically exactly the same as the binomial distribution. The only exception is that we don't have a fixed number of trials anymore. Does that make sense? Yeah, so the number of trials doesn't remain fixed anymore. If we can say the binomial distribution, okay, let me write this down. The binomial distribution approaches the Poisson distribution as the number of trials increases. So as n approaches infinity. So in other words, if you have a binomial situation, success or failure, but if you do this for loads and loads of time period, or if you do this loads and loads of times, loads and loads of trials, n approaches infinity, you should end up with a Poisson distribution. So these two things are related to each other. Yeah? A Poisson distribution is just basically what we call the limiting case of the binomial distribution. So in other words, the binomial number of trials increases, it approaches a Poisson distribution. Does that make sense? Yeah? So in other words, these two things are related. They're still discrete, but if you just increase the number of trials, then you should end up with a Poisson distribution.
Your binomial is fixed the trial.
Absolutely.
But when we increase it, which is not fixed, then it becomes Poisson.
It approaches a Poisson distribution. Yeah, so approaches and becomes are two very different words. Okay, if you increase the number of trials of a binomial distribution, so instead of doing it 10 times, you do it 100 times, it should more look like a Poisson distribution.
But it's not.
It doesn't exactly become a Poisson distribution, no.
Yeah, what's the differences?
So become means that it is exactly the same.
Yeah, I mean, what aspect is different?
You mean?
When we approach to Poisson, what's the differences?
What's the difference between approach and become? So approach means that it starts to look like this. Yeah, it starts to take on the same characteristics as a Poisson distribution. But if it becomes a Poisson distribution, it means it's exactly the same as a Poisson distribution. Forget binomial anymore, you can just use a Poisson distribution. That never happens. But it starts to take on the characteristics of a Poisson distribution.
So the formula will be different from this.
The formula will be different. And actually the way which we consider the formula for a Poisson distribution, you can see it in the slides, is literally by thinking about a binomial situation and thinking what happens as that gets bigger and bigger and bigger. Yeah? So a key word, approach and become. Approach means it starts to take on the characteristics of this thing. Becomes means it's exactly the same as this thing. Is that okay? There is a subtle difference there. Okay. But really the main thing which I want you to take away is that even though we've been talking about two different things today and yesterday, Poisson distribution, binomial distribution, they are related. They are related to each other. Okay? So let's just have a quick look at what we've got left. Okay? So literally, if you wanted to summarize exactly what I just said, it's there on slide 61. As the number of trials increases and the probability of success reduces, you should end up with a Poisson distribution. So, if you wanted to look through the definitions, or if you wanted to look through where the probability mass function for Poisson distribution comes from, look at slide 62 through to slide 65. Yeah. So 62 to 65 is a proof. You don't need to know that. It's quite in-depth. It's quite involved. I recommend you at least have a look at it to show that they are related. Okay. And if you're interested in your mathematics, which hopefully you all are, have a look at that. Okay. But effectively, the thing which I want you to take away, in fact, slide 67. There you go. That's the thing which I want you to take away. Okay. So the box at the bottom there has the probability mass function of a Poisson distribution. Like I say, you don't need to remember this because this is given in the formula sheet. But effectively, the probability mass function is given, I'll try and remember it, is it lambda to the power of x, e to the power of negative lambda over lambda factorial? Or have I got that complete? X factorial. Close enough. Okay. That's the probability mass function. So if you want to find the probability of an outcome given your parameter lambda, that's how to do it. That's in the formula sheet. That's in the formula sheet. Okay. So just because we're running out of time slightly, okay, we'll look at expectation and variance on Friday. Can I ask you, in the meantime, to have a look at slides 69 and 70? There's two questions there. All you need to do is use that probability mass function in order to calculate the associated probabilities. Okay, so can I ask you to have a look at slides 69 to 70? Like I say, if you're interested in where that formula comes from, it is in the slides. Okay, it's quite in-depth and quite involved mathematically, but I think it's well worth just at least glancing at and having a look at. It all stems from the idea that a Poisson distribution is just basically the limiting case of the binomial distribution. Okay, just thinking about that, you end up with this formula here, and this is the formula which you would need to work out the probability of an outcome happening given the parameter which is defined, the rate. Is that okay? So have a look at slides 69 and 70 for me between now and Friday, and then we'll have a look at maybe a couple of questions on Friday. Then we'll move on to expectation, variance, and we're done with probability distributions. Is that okay? Good, fantastic.